lab report, we will learn that Earth's surface is cracked into large pieces called tectonic plates. These plates are slowly moving, creating mountains, trenches, islands, volcanoes, and rearranging continents. And scientists can track the history of the plate movements by analyzing fossils and rock layers. Today, we're gonna visit Vasquez Rocks to learn about plate tectonics. It's about a 1-hour drive north of Los Angeles, and it's a really famous rock formation. Adam, Caroline, are you excited?
Dr. Jeff, field trips are great, but what's so special about some rocks?
Oh, I've seen these rocks before. They're huge. And they've been in movies like Austin Powers, Star Trek, Planet of the Apes. Guys, have you not seen these movies?
Sorry.
Yeah, you guys need to get out more.
Speaking of getting out, we're here. Thanks, Mom, for the lift.
Don't forget your soundbox.
I got it.
Whoa! Those are huge!
Just like in the movies.
Let's go explore. How do you think these rocks were formed? Without looking it up.
Well, usually rock formations have horizontal layers because the sediment is deposited over long periods of time. But these rock layers seem to angle up.
Yeah, I don't think these were formed by just water and wind erosion. I mean, there's no way that wind can move something that big.
Was it tectonic plates?
Yes! How did you know that?
Well, you mentioned the topic back in the RV.
Today, we're gonna visit Vasquez Rocks to learn about plate tectonics. I guess I did.
What are tectonic plates?
They're huge pieces of the Earth's surface that slowly move.
Like they're moving right now?
Right this second. But it's really slow. They move slower than your fingernails grow. But over thousands or millions of years, tectonic plates can move huge rocks out of the ground. They can even rearrange the positions of continents. To understand how it works, let's go back to the RV. This container is a model that has layers of sand to represent ancient layers of rock.
Normally, sediment can be moved by wind or water over thousands of years.
And sediment forms sedimentary rock when it is compacted and hardened by the layers above it.
Yes, exactly. Now watch what happens if I move Earth's surface.
Whoa, it's forming a bulge that looks just like mountains.
Yes, exactly. The movement of the Earth's surface pushed the sedimentary rock layers towards the surface.
Then the layers close to the surface could be exposed by erosion, making
Vasquez rocks.
You got it.
In nature, what actually causes Earth's surface to move?
To understand that, we have to learn about the layers of the Earth. The layer we walk on every day is called the crust. It is made of solid rock. Everything we do is on this layer. The crust is between 5 to 70 kilometers thick, depending on the spot.
So that's 3 to 40 miles.
Under the crust is the mantle. The mantle is about 100 times thicker than the crust, and it's extremely hot, 2,000 to 4,000 degrees Celsius, depending on the depth.
So below us, a few hundred miles down, we would be burnt to a crisp.
It is so hot because when Earth was formed billions of years ago, many small meteors crashed together, forming one large, flaming ball of molten matter called Earth.
So over billions of years, it's cooled down, leaving the surface like it is today. But inside, it's still extremely hot.
The innermost layer is called the core of the Earth, and it's even hotter, over 5,000 degrees Celsius.
That's almost as hot as the surface of the sun.
Yep, and the innermost part of the core is solid because it's made mostly of iron under intense pressure from all the rock above it.
So the inside of Earth being extremely hot rock and under tons of pressure is what causes the land to move.
The process is called convection. It's movement caused by warm fluids rising and then cooler fluids sinking.
Like a lava lamp.
Yeah, the light from the lava lamp causes the wax to heat up and rise as it becomes less dense. Then, when it becomes more dense, it cools down and sinks again.
And the process continues as long as the bottom stays hot.
Exactly. On Earth, convection is powered by heat from Earth's core and mantle. And that process moves large pieces of the Earth's crust called tectonic plates. Speaking of plates, the Earth has 7 major tectonic plates: North American, South American, Pacific, African, Antarctic, Eurasian, Indo-Australian, and...
That's 7.
That was 7. And there's a bunch more that are smaller. But those are the major ones. Check out this map of where we are.
We are next to 2 tectonic plates.
Which makes sense because Vasquez rocks were formed by the movement of tectonic plates.
Exactly. About 20 million years ago, those 2 plates were crashing together, pushing up rock layers like Vasquez rocks. But now, those 2 plates are grinding past each other.
Do these kinds of rocks form everywhere that plates meet?
Actually, what forms mostly depends on what kind of plate boundary it is. There are 3 main types of plate boundaries: convergent, which means the plates move towards each other; divergent, which means they move apart; and transform, which means the plates slide past each other.
The one in this area is called the San Andreas Fault, and it has a history of having major earthquakes.
That's right, and it's a transform plate boundary. Here, the Pacific and North American plate are sliding past one another a few millimeters each year. Take a look at this map of large earthquakes over the last 100 years. What do you notice?
There is definitely a pattern to it. The earthquake locations are forming lines.
And if you connect the lines, it looks a lot like the map of the tectonic plates.
So, earthquakes happen at plate boundaries?
Most earthquakes happen where plates meet. As plates move, their rough edges lock together. Pressure builds, and then boom! It jolts forward, causing the ground to shake, which is an earthquake. If you look at this map of major volcanic eruptions, they also occur mostly on plate boundaries. The next type of plate boundary is the convergent plate boundary. That is where tectonic plates crash together. The best example of this is the Himalayan mountains, which are formed due to the Indian plate and Eurasian plate converging together over 50 million years. Scientists call this uplift, and it's still continuing today. When a continental plate and an oceanic plate converge together, something interesting happens. It turns out that the oceanic plate is more dense, so it sinks down below the land. We call this subduction. This causes deep trenches to form at the boundary and a lot of volcanic activity over the land. The wet rock from the oceanic plate is heated in the mantle and it melts. Then, when this molten rock rises, it erupts into volcanoes. We can see this on the coast of South America, in countries like Chile, where lots of volcanic mountains form on the coast because there's a subduction zone. When 2 oceanic plates come together, one of them usually subducts below the other. The resulting volcanoes that form can create chains of volcanic islands, like the Aleutian Islands off the coast of Alaska. The last type of boundary is the divergent plate boundary, and that's when 2 plates move apart. When this happens underwater, it forms new ocean floor and takes the shape of a ridge. Scientists call it a mid-ocean ridge, and there is a huge one in the middle of the Atlantic Ocean. As the plates diverge apart, new ocean floor is forming.
The Atlantic Ocean is literally getting bigger.
When this happens on land, continents can be split apart. The new land forming in between is at sea level, so the ocean is filling in that space. For example, in the northeastern part of Africa, 2 plates are currently diverging apart.
What was once one continent is slowly diverging into 2. So if all this is happening, then that means millions of years ago, the continents would have been in completely different places.
But there were no modern people here millions of years ago, so how would we even know?
Scientists have some impressive evidence to show that the continents were once positioned way different than the map we all know today. Have you ever looked at the coast of South America and thought that it kind of looks like a puzzle piece that fits right along the coast of Africa?
Actually, I have noticed that.
So did a scientist named Alfred Wegener. But when he told people that a continent might move across an ocean, people thought he was crazy. He needed evidence. Turns out that there are some very specific fossils of land animals and freshwater animals found only in these two regions of the world.
They couldn't have swum across the whole ocean. Land animals can't swim that far, so that means the land might have been connected in the past.
Yes! While impressive, that evidence wasn't enough to support such a big idea. To build his case, Wegener and other scientists also looked at rock layers on the coasts of the two continents. They discovered areas of matching rock layers from the same time period. This also suggested that the continents were connected at some time in the past.
So, the last thing they needed was to explain how the continents were moved.
The tectonic plates. In the ocean between Africa and South America is a divergent boundary, which is what pushed the continents apart.
Exactly! Scientists knew that the rock furthest from the plate boundary is millions of years old, but the rock very close to the boundary is only thousands of years old.
That's evidence that the boundary is producing new rock that is forcing the continents apart.
Exactly! Scientists repeated this analysis on all continents and built a model that looks like this. It shows how the continents were positioned about 230 million years ago. They called this supercontinent Pangaea. In fact, the continents moving apart and then coming back together seems to repeat in a cycle about every 500 million years.
So millions of years from now, the map of the Earth will look completely different than it does today.
Amazing! Now, let's explore the kind of careers you can have studying tectonic plates.
Every year, there are more than 20,000 earthquakes that happen worldwide at plate boundaries. Scientists called seismologists study the patterns of these earthquakes, their sizes, locations, depth, and more, to predict big ones, hoping to minimize damage and save lives. They use instruments like the seismograph, which records data about an earthquake. This information can be used to alert the public, detect patterns, and map activity along the plate boundary. Since most volcanoes occur along the plate boundary, scientists called volcanologists get to study the formation of volcanoes as well as their eruptions. Sometimes they have to get close and take samples of lava to analyze its characteristics. They also study what the volcano looks like underground in order to find ways to predict eruptions, which can save lives. Geologists can study rock layers to better understand the history of the Earth. There are even planetary geologists that study the rock makeup of other planets, like Mars. These are just a few of many careers that study tectonic plates.
Today, I'll show you how to make a model of convection, which is what drives the motion of tectonic plates. To do this, you will need a spoon, a dish, a pan with a hot plate, 3 cups of water, red food coloring, and pearlized shampoo. Pearlized means it forms glitter-like patterns when the liquid moves, thanks to an ingredient called mica. Make sure to look for mica in the ingredients. Start by mixing 1 cup of shampoo into 3 cups of water. Next, add about 20 drops of red food coloring and mix it up with a spoon. When you run your spoon through it, you should see swirls, like this. Now, pour it into your pan, and with an adult present, turn on the heat. You can use your spoon to get rid of some of the bubbles. It's starting to circulate around thanks to convection. The liquid gets heated and rises, then it cools and sinks. We can see this happen thanks to the mica crystals that reflect light as they flow through the liquid. Convection in Earth's mantle is powered by heat from the core, and that's what moves tectonic plates, with one major difference. The hot mantle is solid due to the pressure of all the rocks above it, so it circulates extremely slowly, over years, not seconds like our model. Try it yourself.
Thanks, Adam. Now let's review.
Today, we learned that the Earth's surface is broken into large pieces called tectonic plates.
These plates are slowly moving, creating mountains, trenches, islands, and rearranging continents.
Scientists can track the history of the plate movements by analyzing fossils and rock layers on different continents.
And now you know about tectonic plates. Join us next time on the Lab Report. I'm Dr. Jeff.
I'm Caroline.
I'm Adam.
And remember,
Always question, always wonder.
Let's go. Hit it, Mom.
Oh, we're actually moving.
Imperial sticks,